Good afternoon to you, all of you, Butala. Today, yeah, can you hear me? I know that.
Yes, sir.
Okay, very good. Yeah. So today, 30th April 2022. So welcome to Thermodynamics class semester 2 B2. All the three batches, manufacturing, mechatronics, and BST. Today is the continuation of last week lecture. This about flashing, but I couldn't upload the video yet. So hopefully I will send it today. So flashing and vapor compression cooling technology. So here the key is flashing. So when you know about flashing, yeah, you can understand vapor compression cooling technology very well. Because when it comes to the technologies, it is not the component, but the functionality of those. And there is what you call the refrigerant or the working fluid. The behavior of working fluid, the knowledge of that is very important. Okay. So before that, I'm going to share with you a software. The name is Coolpack, Coolpack software. Actually, since most of you are working students, perhaps knowing of this software may be useful. Coolpack. It's a free download. It's a free download. Let me share my screen. It is something like this, the Coolpack. Coolpack software. Lot of information, data are there. So all in one. So it is very easy. Example, let's say if you need to get the properties of water. Okay, maybe saturated properties of water. So you can go to here, SAT saturation. Here, many substances. So you can look for water. Is water. So you can get the saturation properties, the temperatures, pressures, even specific volumes, enthalpies, and R value, okay? And also you can see the entropy values. So this is very important. If you know how to read this, and if you can understand this, you can see plenty of data is here. This is about water. And let's say the same way, if you need to get a chart, even your pH, TS, or even other one, maybe HS. Let's say pH or TS chart. You look for water R718. You can have this. So all in one. It is very, very useful. Okay, that's why that's the advantage of having Coolpack. So let's say you have heard about refrigerants. So if we look into R134A, the pH chart, you can see here. So this chart, if you can understand this, would be very good. Okay. So even you can analyze some pH diagrams as well. Okay, later we will learn about this. Also, if you think of drawing something, so you can make use of this. Okay, so I just show this. So there are many. Oh, this was not updated. So you can go for the latest one. Even the refrigerant calculators. Oh, see here, refrigerant calculators. So this is to find the properties and all. You can explore this. Anyway, this is a free software. This is a free software. So you can have this free software. So the later we will use this data whenever we need. Look for this. So this is about cool pack. Okay, good. So try to download this. You look in the web, the free download of cool pack. This is from Denmark Technological University, Technical University, DTU. Okay, DTU, Denmark Technical University. So they developed this. So many are using this, very useful. You can have this and it is very handy tool really. Okay, good. So saturation properties of liquid refrigerant. So this is for the refrigeration applications. So let's say saturation properties of liquid refrigerant. Saturation properties. Okay, liquid refrigerant. Sorry, bit noisy. This from the web. So you all know about R134A. At least you have heard this. So example here. I will take R134A. So here, you can see a portion. I just put here. Below this may be liquid refrigerant. Sometimes you have used this maybe. So let's say below this line, maybe liquid. Above this may be vapor. Okay, it's interesting. Liquid. And above this line, let's say vapor. Means both liquid and vapor here. So two phase, okay, two phase. So let's say here, the temperature is 32, or let's say 30 degrees Celsius temperature. Temperature equals 30 degrees Celsius. Celsius. What is the pressure? What is the pressure? What's the pressure? So the substance is R134. At saturated means vapor and liquid both are there. At saturated condition. Okay. Condition. Yes. Then look for saturation properties. You look for saturation properties at 30 degrees Celsius. You will get the answers. Okay, vapor and liquid together means the two phase, consider it's under saturation. Okay, good. So saturation, let's say. Now you have to look for the saturation properties. So what I will do is, I go to cool pack. And I look for the properties, saturation properties, R134. Otherwise, I have to download separate PDF files, look for all, but here all one shot. So I think in your smart device, you can say this. So I will look for 30 Celsius because first column is 30, sorry, temperature in Celsius. Second column is pressure in bar, that is absolute pressures. So I will look for 30 Celsius. See 30, I bring it to the top. So this line, all saturation properties. So I need to look only the pressure, but I will take entire thing. Paste it here. So $30, that is 7.701 bar. Here you can see, if I make it, you can see pressure is 7.701. So pressure is 7.701 bar. This is pressure. This absolute pressures. I think I shared with you absolute and the gauge pressures earlier. So this is the pressure. So very high pressure, you know, quite high pressure. Quite high pressure. How high means in a tire pressure is less than 2 bar gauge pressure. So absolute is below 3 bars. So here 7.701 bar, high pressure. So this is the usage of saturation properties. So you can have the other values as well. Later we will look into that. So you know, this is very high pressure. And here two-phase liquid and vapor. So now I will go for a new slide. It's okay. Vapor, liquid. Below this red line, liquid. Above the red line is vapor. Because maybe I will do this way. vapor and liquid. Vapor and liquid. So if this is R134A, okay, let's say at 30 degrees Celsius. At 30 degrees Celsius. So the pressure is P absolute is 7.701 bar. So we can simply say pressure. That is okay. One bar. Okay. Then the gauge pressure is P gauge is P absolute. Okay. P absolute minus P atmospheric. So you may be using this P atmospheric. So P gauge means if you put the gauge here, this is P gauge. Okay. So this is P gauge. P gauge. So P gauge is measurable separately, and the atmospheric pressure is also measurable. So you know P gauge, you know atmospheric. So P absolute is P gauge plus P atmospheric. Okay. So if you know P absolute means P absolute ABS P gauge plus P atmospheric. Atmospheric pressure is measurable. The barometer, whatever, there are ways and means of measuring the atmospheric pressures. I believe you have some little idea about the gauge pressures, two-phase. And now with this saturation or saturated properties, if you know the temperature, because that's measurable quite easily, then you can even have the other values from the tables. Other values. And I take this out. Okay. I believe you can understand this. Let's see how we are going to connect this with our application of what? Flashing and vapor compression cooling technology. How we are going to connect this? Okay. So back to last week discussions. Last week we learned about flashing. Different ways we have learned flashing at high temperatures, even flashing in liquid fuel and all, and also flashing applicable for cooling technologies. Okay. Before that, okay, that is fine. This is a pipe, a piece of pipe. Last week discussion. Here, I'm going to draw the nozzle, not to say nozzle, this is a different one. A plate here. So in this plate, at the center may be small hole. Yes. The same thing. If I draw this way, a cross section maybe. A cross section. So I will continue this. So when you apply suction, okay, when you apply suction, what happens is the liquid above this tiny hole or a restriction for the flow. This is a flow restriction. So because of this suction, this liquid overcomes flow restriction and passes through this restriction and come to the other side. Okay, but one thing for sure, this side become low pressure or reduced pressure. So significantly reduced pressure reduced. So as a result, say liquid comes, and not only the liquid, and there can be even some gaseous molecules also come. So I will mark the gaseous molecules in a different color. Yeah, should be okay. So gaseous molecules and liquid molecules, both are together, but of course more liquid in general. So this is the situation when you apply suction. So these gas molecules, okay, before turning to gas, it is liquid here above this flow restriction, but once passed through here, turns into gas. So this is the point now. So I believe you can understand this. This is the flashing. What way? Explain flashing. Flashing of liquid by means of passing through the flow restrictor under a suction, okay, or low pressure, under low pressure. So this happens. Okay. Reduce pressure. And if you take this, if you take this, you can consider this as vape and liquid at same pressure, of course. This can be considered as vape and liquid under same pressure. So let's say now reduce pressure. So see, reduce pressure. Let's say pressure reduced to 1 bar. Reduce pressure. So see, reduce pressure. Reduce to 1 bar. One bar. Let's say not 1 bar, maybe 1.5 bar. Absolute. What is the temperature? Because vape and liquid together. What's the temperature? Okay, what's the temperature? So before talking about temperature, we should know what substance is this? What liquid substance is this? So we have to know that upfront. Because if you do not know the liquid, the type, we cannot comment anything on pressures unless it's being measured. Okay. So therefore, let's say this is R134A. R134. So now here above the flow restriction, later we will talk about the pressure, but below the flow restriction, let's say this is 1.5 bar absolute. Now we have to look for the pressures, sorry, the temperatures for 1.5 bar absolute. What's the temperature? You have to go for R1348 table. It's here 1.5 bar. Maybe somewhere here. We have 1.448, 1.511. So it is 1.511. Let's see, somewhere here. One 1.511. I will take the entire row. So at 1.448, it is minus 18. 1.511, it is minus 17. So 1.5 may be minus 17.5. Okay. Minus 17.5 degrees Celsius. So you got the point. Okay. So slowly we are building up this cooling technology concept out of learning the flashing phenomena. By means of passing through a flow restriction under a suction. Okay, suction means it's reduced pressure. So you have to apply a suction. Reduced pressure means suction. That's a practical way of having a reduced pressure. So suction. I just put this. Okay, good. So you know this. Now let's say I'm changing the pressure to 1.2 bar. Or let's say 1 bar. Now what is the temperature? 1 bar. So you go to this at 1 bar. Yes, you have 1.020 and 0.974. So minus 26 to minus 25. So let's say this is minus 25.5. Minus 25.5. So temperature is minus 25.5 at 1 bar. Let's say 2 bar. 2 bar. What's the situation? So you go here, table 2 bar, because vapor liquid together, that's the point. Don't forget. This is two-phase, vapor and liquid coming out here. So this is, yeah, two-phase. Okay, see. So 2 bar. Yes, we have 2.007 minus 10. So I will put here minus 10. Okay, minus 10.5. Okay. let's say minus 10 degrees Celsius. And then maybe I will go for 3 bar. Okay, 3 bar. Two phase, 3 bars. Here is 1 degree. 1 degree plus 1 degree. Okay. So afterward, let's say minus 2.5.5 temperature. So this is very cold. Minus 25.5, very cold. So this can, as this is minus 25.5 means very low. So you can use this for very low cooling applications. Okay. Low temperature, deep freezing, minus 25, you can use for deep freezing applications. So low pressure, low temperature. So this is a kind of not ultra low, but this is considered low temperature application. Low temperature, what application? Cooling application. Because minus 25, even if you touch by hand, your hand will be solidified. Your blood flow will stop. Okay. Cold burn. So low temperature cooling application means, let's say this is freezing. So defreezers and all. Freezing application, this minus 25 is okay. So minus 10 means minus 10 temperature normally consider not a low temperature, but a medium temperature application. Medium temperature. So this can be used for chilling, or how to say, this is not deep freezing, chilling, or moderate freezing. Moderate freezing also not good. A chilling application. Minus 10. Okay. You can use for chilling applications. And this is minus 10 medium, plus 1 means this is something like high temperature application. Cooling application. Let's say this is chilling, and also maybe chilling. Or even air conditioning applications, you can use this temperature maybe. So generally, when it comes to cooling applications, if I compile all this into one slide, you have low temperature applications. You have medium temperature applications. You have high temperature applications, but all coming under cooling technologies. So common phenomena, but quite interesting. Yeah. Low temperature, medium temperature, high temperature. So this may be the beginning of learning of on cooling technologies. So here we'll go for a new slide. Later I will add a title for this. Let's say if you can maintain a continuous process like this, a continuous process, continuous process. So you can continuously use this low temperature two phase, okay, for cooling purposes. So how you are going to do is you direct this flow, okay, direct this flow for a cooling application. Okay. Example, maybe a refrigerator. Maybe refrigerator. Here. So you direct this flow. Okay, you direct this flow, and here there can be a cooling plate example. Cooling plate. So this may be very cold. Okay, this may be very cold. So you can have a cooling space here. So what's the temperature? We'll go for minus 10 or minus 17 maybe. Here we have minus 17.5. So we will go for temperature minus, let's say 17 degrees Celsius. Kutala, you should try to understand this. Huh? So space. So this may be a refrigerator. So minus 17 degrees Celsius. So this two phase will be passing here. Two phase. Okay. Two phase. So passing here minus 17. So then after that, what happens is, so you in this two phase, then out here, somehow, after experiencing, this can be out. I just put here. So this plate. So pass through the plate. This refrigerant can be out. So after that, this will go back here continuously. So you have to have a suction now. So suction can be applied here. Suction, apply suction. Apply suction. Then this apply suction. So here also suction. Here also suction. So you apply suction here. This is a continuous flow passage. Okay. This is a continuous flow passage. So suction here. So let me do this way. Sometimes when I explain too much, even can lead for confusions. So suction is here. Okay. Oh, sorry. You can't see the slides. Can you see the slides, Puta? Then payno ned.
House.
Okay. Apply suction. I think you already got the concept now. Apply the suction. All sealed passage. See, well sealed passage. Be patient, Puta. So well sealed passage. So all fully sealed. Otherwise, we cannot maintain suction. So then this flow pass through here. All the way here. All the way here. Okay. All the way here. Then wind pass through this. And what happens is, after passing through this, so all will become gas, because all will become gas because gas. All will become gas. So you apply suction here. This suction applying also affect the suction here. Okay, so this is the way. So gas means already received heat. So whatever liquid passing here, whatever liquid passing here turns into gas. So heat will transfer. Let's say this minus 17 is here. Minus 17. And here also minus 17. Here also minus 17. Minus 17. Very nice. Here also minus 17. Okay. Here also minus 17. So here also minus 17. They are also minus 17. And inside here, in this application, this cabin may be in minus 10. So minus 10, minus 17, you can see heat transfer from cabin to here. Heat transfer. See, heat transfer here. Because minus 17. Minus 17 C is the temperature here. Cabin is minus 10. So let's see, if you need convenience, I just put plus 10 here. Temperature, let's say this is minus 10 for your easy understand. So positive temperature, negative temperature. So sugar transfer here. So minus 10 and minus 17. Minus 17 is more cooler. So towards more cooler substances, this heat transfer. And finally, because of this heat transfer, this liquid turns into gas. Finally, full gas is being sucked out from this flashing device through this cooling plate. So this cooling plate, we can name this cooling plate as, because all the liquid disappears. So, and all the liquid turns into vapor. So this can be named as evaporator. Okay, this can be named as evaporator. Because the process undergoes is evaporation. So evaporation process take place. So I put it as evaporation. That is fine. Eh? So I will change this to more pleasant color. Yeah, good, good. It's a more pleasant color. Good. So this is evaporation takes place here. Nice. Evaporation. So you apply suction here. So then this flashed two-phase flow will pass through this cooling plate or cooling element, and then this two-phase fluid, liquid and vapor, comes in, but the vapor is there and all the liquid turns into vapor. So 100% vapor. So evaporation takes place. Okay. So suction is here as well. So everywhere suction takes place. Here also suction being applied because suction apply here. So suction effect is there. Here, everywhere here. Okay, good. Then I just put it here. Later I'm going to use that. So R134A, here, it is something like this. See liquid here, until this level liquid. Let me take this. See liquid is here. And here should be liquid because if no 100% liquid here, there is a problem because flashing is not perfect if no liquid is here. So here we call this flow restrictor. Here you can see flow restrictor here, a little tiny passage sealed with liquid up front. So we call this liquid seal. Liquid seal. You are learning a lot actually. Liquid cell. So having liquid cell means here can be gas. Possible. Here can be gas. But there it should be all liquid below, and here can be gas and liquid, both possible here. Let's say I think better I put this way. So let's say here can be gas possible, and here becomes liquid. So by right, so coming into full liquid means here can be like this. Let me put. Because two phase possible here, but here is liquid cell. So yes. So this area is something like this. Okay, something like this. So vapor and liquid equilibrium takes place here. Okay, but here should be liquid cell definitely. So here vapor liquid equilibrium, even here. Also like that. But here low pressure. So anyway, I take this out here. So I put here vapor liquid equilibrium. Everywhere I see here, but here is high pressure. Let's say this can be 30 degrees Celsius, vapor liquid. Okay, 30 degrees Celsius vapor liquid. The pressure here, 7 bar. So I need that only. 7 bar pressure. Seven bar. Imagine. Seven bar. 30 degree. Here minus 10. What is the pressure as minus 10? Yeah, you can send the attendance. That's all right. 7 bar. It is 37.7. At minus 10 pressure, two bar. See, 2 bar. So here. Seven bar. This side at -10. Two bar. Okay, two bar. Very nice. So this is 7 bar. So for continuous process, continuous process, continuous process, to have suction here. After that, continuous suction. So you must have a device to suck this, and for continuous operation, suck this and pump back to high pressure. So there we use a compressor. Okay, compressor. So I put a compressor photo, maybe a simple one. This is not the air compressor, but this is for refrigerant compressors or special designs. Okay, very special designs. So let me put a photo. I just put this photo. So this device can apply suction. Okay, this device can apply suction. And there is a suction inlet. See this pipe. And after suck this pumps from the outlet. High temperature. flow passage. So here may be gas, high temperature gas. You can see here, all high temperature. High temperature. Then slowly cools down along this passage. Okay, slowly cools down and finally all turns into liquid here. So here you can see all the high temperature gas. Finally become more and more liquid. So you can see the gas turns into liquid. See, more liquid appears. Okay, more liquid appears here. Nice. So here, when more liquid appears, means all the gas will be turned into liquid afterward. So here turning gas into liquid is something like condensation. Okay, the condensation process takes place. So same like evaporation here. The condensation takes place here. The condensation takes place. Okay. Then here, this device, suction and compression. So suction and compression, but here we put only compression because for compression, naturally you have to suck the gases and then compression takes place. So here suction takes place and then the suction and compression. So I just put suction here. Condensation. Compression. Very nice. Suction. This is liquid seal. So here what takes place is flashing. So in the flashing, it's a very nice phenomena. In the flashing, you have a tiny liquid droplet will be turned into gas. So relatively the gas, the equivalent volume size is quite big. So you know this, huh? I explain in flashing. So a small liquid volume turn into a huge gas volume. So you can see this liquid turns into full gas. We can term this as flashing or expansion. Another word, flashing or expansion. Nice. This is what's taken place at the liquid seal. Very nice. Okay. This is good. Put this somewhere. This picture. So you can see low pressure side. See R134 at -10. See 2 bar. At 30, two phase again, same like here, 7 bar. So you have a high pressure side and low pressure side. High pressure side and low pressure side. See, just below this flashing through this restriction or pinhole, low pressure side starts. Until the suction. The low pressure side starts. So compressor suction, and here at the liquid seal, you can see low pressure side. Above this is high pressure side. So for the high and low pressure sides, the responsible processes are this flashing and this suction and compression takes place at compression. So these are the two components responsible for this high and low pressure sides. The flashing phenomena, and here suction and compression phenomena. So suction and compression takes place at compression. So compressor and the flow restrictor or flow control or expansion device. So expansion device and compressors are the two elements responsible for this high and low pressure, and to utilize this flashing effect. So you can see vapor compressed, condense, flashing, suction again, and evaporates and turn into fully gas and back to compression. So we call this vapor compression cooling system. Okay. So vapor compression, refrigeration or cooling applications. So we have not identified the components yet, but I believe you can make use of this for your improved understanding. I'm very sure you have learned about refrigeration. I know how you have learned refrigeration. It is not this way. You never learn about the liquid seal. You have never learned, I'm very sure. Okay. But that is extremely important. The knowledge of liquid seal is the secret of cooling technology. The knowledge about this flashing is the secret of cooling technology. But perhaps you realize this now only, maybe. So only if you understand in this way, you can develop the cooling system. Any cooling system you can develop. So I extend this until here maybe. Okay, anyway, let's leave this. Some basic understanding. So this should be the basic phenomena. Next week, I will complete the refrigeration with some analysis, and also we will learn about some cooling systems as well as the energy balances and the open thermodynamic systems, open systems. We will look into next week. For these 2 hours, I believe this is enough for today. If I summarize this, flashing and vapor compression cooling technology. Cooling means refrigerants. So cool pack. The knowledge about this software makes you pretty comfortable using data for two-phase. Yes, two-phase. Using that cool pack data at 7 bar. 30 degree at 7 bar. Vapor liquid together. Saturation properties. Saturated properties actually. Yeah? That's okay at 30. So this can be modeled like this. So together. See, flow restrictor here comes down. So vapor liquid at 1.5 bar, there is a certain temperature, maybe minus 17 there. 17.5. 1.5 bar absolute. Sorry, 1 bar minus 25.5 low temperature application. 2 bar minus 10 medium temperature cooling applications. 3 bar plus 1 high temperature applications. So there are 3 types, low, medium, and high. We can generally categorize because components, they refer this for the selection of compressors and all. So we have developed this. Where we start? 1 here. Evaporation 2. Suction and compression 3. And of course, condensation is the last to develop. Not to say the last, but together with the compressor and the condenser, we develop together here. See, vapor liquid together. You know the gauge pressures and absolute pressures. The processes, flashing or expansion, evaporation, suction, compression. So this is the compressor effect and condensation. So you can see some key thermodynamics processes are here. You can see it. So that's all for today. We have developed until here. So later, next week, we will complete somehow up to manageable level knowledge, at least to understand the system and do some improvements, so provide some suggestions, so do some analysis, improve the components. So you have to have this basic knowledge that is extremely important. And one more thing I forgot to mention you. This fluid passing through these components and all, actually this fluid is the one performing. We call this working fluid. At one place it's flashing, another place that fluid evaporates, another place suction takes place, subjected to low pressure, say, of course suction, and then the compression takes place, then condensation. And this fluid undergoes different phases, temperature, pressure changes. So actually this fluid is working. What's performing is this fluid. So we call this working fluid. And all the components are supporting this working fluid to perform in this cyclic continuous way. So that's why we call these refrigerants are working fluids. So very nice. So that's all for today, and I think it's 3:30 Butala. So thanks for joining, and make sure only 30 plus students join this Google Classroom. So I'm going to post some notice assignments, but to make sure that you are receiving the right knowledge. So make sure you get enrolled into the Google Classroom, because I'm posting some work over there. Okay, very good. So, any questions before stopping the class? Did you understand something? Actually, understanding is totally, you need some good effort from your side. With the support of this, you can have a better understanding. Okay, so try to attend the lectures, try to follow this with your prior knowledge, because you are weekend students. So you have some experience, connect this. You may have better experiences in cooling technology. Yes. So you can connect this knowledge, and we will try to understand completely the cooling system. I first start with refrigeration because BST students, they have to know refrigeration very well. Mechatronics, yes. Manufacturing, yes. And BST and mechatronics, this is the first and the last chance. So at least we should know some important applications and application related phenomena related to thermodynamics. That's why we just touch with thermodynamics and start with the simple phenomena of flash. Later we will do analysis. I hope this knowledge should be useful to you, and see you next week, and take care all of you. So wish you all good luck, and see you next week. Take care, and make sure to get enrolled into the thermodynamics Google Classroom, and the representatives kindly assist your batchmates for that. Okay. See you next week then.
Thank you, sir.
Okay, Bhutala, bye.
Thank
So you are learning
sir.
technology. Learning technology is something,
Thank you, sir.
okay? So try to learn at your best levels. Then you can make use of this knowledge and you can do wonders. See you next week, Bhuta. Thank you very much for joining the class today. Bye then. Bye.
Thank you, sir.
Thank you, sir.